Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is the maximum power transfer theorem as applied to DC circuits. Our objective today is to learn at which conditions a circuit delivers maximum power to a variable load resistor. Additionally, we'll discuss efficiency at and at other than maximum power conditions. This lecture operates under the presumption that you are marginally skilled in Thevenin's theorem, and to a lesser degree Norton's theorem and source conversion. If you're not familiar with these theorems and techniques, please take the time to check out these lectures, available at the Big Bad Tech channel. Additionally, this lecture makes use of spreadsheet and graphing software, particularly MS Excel. This or an equivalent software resource makes an incredibly handy instructional resource when visualizing circuit properties at or near maximum power conditions. Bottom line up front, a variable load resistor will receive maximum power from a circuit when its resistance is exactly equal to the Thevenin's equivalent resistance for that circuit. This is to suggest that maximum power is delivered to the load when RL equals RTH. As we'll soon learn, this isn't exactly the most efficient of conditions, but does however represent peak power delivery conditions to the variable load resistor. Consider this series parallel circuit supplying variable load resistor RL. RL will receive maximum power when RL is exactly equal to the Thevenin's equivalent resistance for this circuit. By all means, pause the lecture and use Thevenin's theorem to find the Thevenin equivalent voltage ETH and the Thevenin equivalent resistance RTH. If you've applied Thevenin's theorem correctly, you should have obtained the following values. ETH is a 12-volt source, and RTH is a 240 ohm resistor in series with the variable load resistor RL. Again, this lecture operates under the presumption that you are skilled in Thevenin's theorem. If you need help with Thevenin's theorem, by all means, watch the Thevenin's theorem lecture available at the Big Bad Tech channel. Of note, one could also perform a source conversion on the Thevenin equivalent circuit to obtain the Norton equivalent circuit consisting of the Norton equivalent current source IN with a value of 50 milliamperes and the Norton equivalent resistance RN equal in magnitude to RTH, in parallel with the variable load resistor RL. We can therefore extend the description of maximum power conditions to the Norton equivalent circuit, where RL receives maximum power from the circuit when RL is exactly equal to RTH, which is exactly equal to RN. When RL is set to 240 ohms, note that the Thevenin equivalent voltage source, ETH, sees 2 times 240 ohms, or 480 ohms of total resistance. The voltage divider rule states that equal resistances in series will each drop half the supplied voltage. In this case, the load resistor will experience a voltage drop of 6 volts. Any permutation of Ohm's law will support this time-saving step. At maximum power conditions, the voltage drop across the variable load resistor will be equal to half of the Thevenin's equivalent voltage. From the Norton's equivalent perspective, it can also be stated that half of the Norton's equivalent current will travel through the load resistance. When presented with two paths of equal opposition, the current divider rule states that equal resistances in parallel will draw half the supplied current, in this case 25 milliamperes. Any permutation of Ohm's law will support this time-saving step. At maximum power conditions, the current through the variable load resistor will be equal to half of IN. If one was limited to solely the Thevenin's equivalent circuit, one could use Ohm's law to solve for the current through the variable load resistor RL to also be 25 milliamperes. If one was limited to solely the Norton's equivalent circuit, one could use Ohm's law to solve for voltage across the variable load resistor RL to also be 6 volts. The power dissipated by the variable load resistor RL is the product of the voltage across it times the current through it. In this case, RL is dissipating 6 volts times 25 milliamperes, or 150 milliwatts of power, which represents the peak power this circuit is capable of delivering to a variable load resistor. If RL was set to any other value, lesser or greater, it should dissipate less than this amount of power. Prove this to yourself by randomly setting RL to some other value and perform the same analysis. For the purposes of this illustrated example problem, I'll randomly dial RL down to 120 ohms, or half the Thevenin equivalent resistance. At these conditions, RL, being a smaller resistance, draws more current at 33.3 milliamperes, however drops less voltage at 4 volts, and therefore dissipates less power at 133.3 milliwatts. I'll switch tactics and crank RL up to 480 ohms, or twice the Thevenin's equivalent resistance. At these conditions, RL, being a larger resistance, drops more voltage at 8 volts, however draws less current at 16.7 milliamperes, and therefore dissipates less power also at 133.3 milliwatts. That's the point. At maximum power conditions, RL is at a point when two interrelated values, voltage and current, form a maximum power product. This is where spreadsheet and graphing software become extremely handy, enabling visualizing the maximum power transfer theorem. If I was to plot voltage drop and current draw as a function of load resistance, I would obtain the following graph. At short circuit conditions, when the variable load resistor RL is adjusted to 0 ohms, current, the blue curve, is at a maximum of 50 milliamperes and precipitously decreases as RL increases. In simulated open circuit conditions at the far right of the graph, when RL is in effect infinite, no current will flow. The voltage curve in red is just the opposite. At short circuit conditions, when the variable load resistor RL is adjusted to 0 ohms, the voltage drop across it is 0 volts, and it rapidly increases as RL increases. In simulated open circuit conditions where RL is in effect infinite, voltage increases to the maximum of 12 volts. In short circuit conditions at the far left, 50 milliamperes of current flows through a 0 ohm load resistor, and the load resistor exhibits 0 volt drop. In these short circuit conditions, power dissipated by the 0 ohm load resistor is 0 watts. In approximated open circuit conditions at the far right, 12 volts is dropped across the load resistor, yet 0 current flows through it. In these open circuit conditions, power dissipated by the infinite load resistance is 0 watts. In between these two 0-watt regions is where the magic happens. Traveling left to right from short circuit conditions to open circuit conditions, current decreases and voltage increases. However, in traveling from short circuit conditions to maximum power conditions, where RL equals RTH, power, the product of current and voltage, rapidly increases. From this maximum power condition to open circuit conditions, power steadily decreases. Regions on the low side shoulder of the power peak experience more current draw, but less voltage drop. Regions on the high side shoulder of the power peak experience more voltage drop, but less current draw. The maximum power point is a compromise condition in which two interrelated voltage and current values form a maximum power product. Note that the power curve peaks out in the region of 240 ohms as expected. Load resistances on either side will experience less than the maximum 150 milliwatts we calculated earlier. Regions where RL is on one side of the peak, like our two representative examples at 120 ohms and 480 ohms, will be in the shoulder regions of the peak curve. The maximum power transfer theorem really is this simple. A variable load resistor will receive maximum power from a circuit when its resistance is exactly equal to the Thevenin's equivalent resistance for that circuit. The only tricky parts are 1, obtaining the correct Thevenin's equivalent circuit, and 2, using it correctly. Note RL is but one of two resistors in our equivalent circuit, the other being RTH. Again, at maximum power conditions, RL drops half of ETH and experiences half of IN. The other half of ETH is dropped across RTH, which also experiences the same current. This is to suggest that at maximum power conditions, RTH dissipates equally as much power as RL, and the Thevenin's equivalent source is actually delivering a lot more power than what is being put to use, which leads us right into a discussion on efficiency. It needn't be surprising that maximum power conditions aren't efficient conditions. One wouldn't consider using a dragster to perform the daily commute, nor would one consider entering a Prius in a tractor pull. Not only would you lose, you'd look like a total nerd doing so. Maximum power conditions are as inefficient as efficient conditions are less than powerful. At maximum power conditions, the Thevenin equivalent resistance RTH would also drop 6 volts and experience 25 milliamperes of current. This means RTH also dissipates 150 milliwatts of power. This is to suggest that the source is delivering 150 milliwatts of power to both RTH and RL, or 300 milliwatts. Only 150 milliwatts, or 50% of which, is being put to use. Again, efficiency is the ratio of usable power output obtained from a given power input. Of the 300 milliwatts delivered to the system by the Thevenin's equivalent source, only half of them, or 150 milliwatts, get put to use. At conditions other than maximum power, this efficiency measurement changes. Consider a case in which RL has been adjusted to twice that of RTH, or 480 ohms. During these conditions, the voltage across the load equals 8 volts, and current through the load equals 16.7 milliamperes. Therefore, power dissipated by the load resistor is approximately 133.3 milliwatts. The source, however, is delivering the Thevenin's equivalent voltage of 12 volts times 16.7 milliamperes, or 200 milliwatts to the system, 133.3 milliwatts of which are being put to good use. The other 66.7 milliwatts of power are dissipated by RTH and are considered a loss to the system. In this case, power delivered to the variable load resistor is less than maximum power conditions. However, it's now being used more efficiently. If one was to overlay a graph of efficiency and power, one would find that at maximum power conditions, efficiency is a paltry 50%, however increases as resistance increases. At conditions other than maximum power conditions, power delivery is less than maximum, but depending on which side of the maximum power condition you're on, efficiency can be more or less than 50%. Let's bring this lecture to a close with one more illustrated example problem. This time we'll rip through it without a lot of mumbo jumbo. Consider this series parallel circuit supplying variable load resistor RL. By all means, pause the lecture and use Thevenin's theorem to find the Thevenin equivalent voltage ETH and the Thevenin equivalent resistance RTH. Once you've obtained these values, determine at which value RL will receive maximum power and determine the voltage drop across it, the current through it, and the power dissipated by it at this condition. Additionally, determine the voltage drop across it, the current through it, and the power dissipated by it at conditions when RL is 1/3 of RTH, and again at 3 times RTH. Calculate efficiency at all 3 load resistance conditions. If you've got access to spreadsheets and graphing software, you may want to try and plot a couple values out and get a feel for what the voltage, current, power, and efficiency curves look like. If you've applied Thevenin's theorem correctly, you should have obtained the following values. ETH is a 40-volt source, and RTH is a 500 ohm resistor in series with a variable load resistor RL. At maximum power conditions, RL will equal the Thevenin equivalent resistance RTH. When RL is 500 ohms, it experiences a voltage drop of half of ETH, or 20 volts, and half the Norton's equivalent current at 40 milliamperes. This represents a maximum power product of 800 milliwatts. During maximum power conditions, RTH also dissipates 800 milliwatts, meaning of the available 1,600 milliwatts, or 1.6 watts delivered by the source, only half of it, or 50%, gets put to good use. When RL is equal to 1/3 of RTH, or approximately 166.7 ohms, it experiences only a 10-volt drop. However, current increases to 60 milliamperes. Current has increased, but voltage drop has decreased. This represents a power product of only 600 milliwatts. During these load conditions, the source is actually delivering 2.4 watts of power, where RTH experiences a voltage drop of 30 volts in the same current draw and therefore dissipates 1.8 watts of power, which is written off as a loss, meaning of the available 2.4 watts delivered by the source, only 25% get put to good use. When RL is increased to 3 times RTH at 1.5 kiloohms, RL experiences a voltage drop of 30 volts and a current of only 20 milliamperes. This represents a power product of only 600 milliwatts. Voltage across the load is higher, but current through it is lower. The power product is therefore less than maximum power conditions. During these load conditions, RTH experiences a 10-volt drop in the same current draw and dissipates 200 milliwatts of power, which is written off as a loss, meaning of the available 800 milliwatts delivered by the Thevenin's equivalent voltage source, 75% is put to good use. In this case, efficiency did increase. However, power dissipated by the load is less than maximum power conditions. Here's a look at the current, voltage, power, and efficiency curves for this circuit. Notice power peaks out when RL equals 500 ohms. Regions on the left shoulder experience more current but less voltage. Regions on the right shoulder experience more voltage but less current. The maximum power point represents a compromised condition in which two interrelated quantities, voltage and current, form a maximum product. Alright, that's it. In conclusion, we learned a variable load resistor will dissipate maximum power from a circuit when its resistance is exactly equal to the Thevenin's equivalent resistance for that circuit. Additionally, we discussed efficiency and took a look at voltage, current, power, and efficiency curves for varying load resistances. Remember to review these concepts often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.